Today I'm going to use Harmony Connect to secure data on the blockchain. Harmony from Factom.com is an easy-to-use enterprise blockchain solution that involves no cryptocurrency. Its simple API allows you to start writing data immediately without having to set up any back-end nodes, databases or servers. Its documentation uses the example of a drone supplying GPS location data. I'm going to replicate this example using a real hardware solution. I'm going to use a $10 Raspberry Pi Zero and this $30 GPS module. The Harmony Connect documentation steps you through to your first signed entry in 5 steps. I'm going to show you how to do it in 3 steps whilst improving the security. In Harmony's 5-step example, Step 2 teaches you about creating key pairs and cryptographically signing data. Step 3 revolves around identity and warns about the dangers of identity theft. It describes the method of revoking an identity should it become known that it has been compromised. If we can eliminate the possibility of identity theft in the first place, then steps 2 and 3 become redundant. So how do we do that? This is the signed at source module from TFA Labs. It has its own secret identity and will never give it up, not even to me. It will also do the signing internally. It has to keep the identity secret, taking just milliseconds even on battery power. This saves a whole lot of security headaches, work and worry for the developer. But most important of all, it excludes any doubt later on that an identity has been compromised. The SMD version of the signed at source chip is small enough to attach to existing hardware solutions. Adapter boards can be quickly manufactured for any application, and I have one here already made up for the Raspberry Pi. This particular one has room for my GPS module. So let's get started. So that's the hardware complete and we can boot into Linux. Now we need software to make it work. This can be broken down into 3 components: GPS acquisition, signing the data and writing to Harmony. Getting the GPS data is as easy as opening the serial port and reading the data stream. I will demonstrate that now using Minicom. How you go on to process this data can be as simple or as complex as desired, but it's beyond the scope of this video and it doesn't really show you what's happening anyway, so I will just trigger the process manually from the command line. Harmony has a REST API, so it is easy to integrate with just about anything. There are language SDKs available including JavaScript, Java, Python and Go. As C# is my language of choice, I wrote my own library and released it as open source under the Factoid Authority. This is what we will use now. Let's make a simple command line console app. I'll add in the Harmony Sharp and IOT-SAS packages from NuGet and write the code. I have written 4 command line functions. The first one is to get the public ID. This queries the IOT-SAS module for the public ID and then returns it to the console. The second function is to create a new chain. This happens when we post our first entry. So we first take the data from the command line and enter that into a new entry data class. I should first explain what an entry looks like. I'll take this example from the Harmony documentation. It is made up of an array of external IDs and your data. External IDs are like metadata, fields of information that describe or validate the data contents. You can populate them as you like. Typically, you would sign all the data together and add the signature as an external ID for later verification. It is important that every entry is unique. So in this demonstration, I will be adding in an external ID with randomized data. We then add the ID of our chip, add some random data, combine all the data, and then request the SAS chip sign it for us. That is then sent to the Harmony REST API, and in return we get a chain ID. The third function is to write an entry to our existing chain. This is done in the same way as creating our first entry, except this time we are providing a chain ID. And lastly, the list function queries Harmony for a list of all the entries in a given chain ID. This we will return to the console. I will first query the SAS module for its public ID to make sure it's working. I will now create a new chain by submitting some data. Test 1. We now wait for Harmony to return the chain ID and the hash of the first entry. I guess to be authentic as a drone tracker, I should put in GPS coordinates here along with its altitude and speed, but you get the idea. I will copy this chain ID to the clipboard. Now I will write the second entry to the given chain. And a third entry. If I use our list command, a request will be made to Harmony to return the contents of the chain. I opted to list the entry hash and the content data for each entry. You can get the full entry by simply requesting it using the entry hash. This data is returned from the Factom blockchain, so it can never be tampered with and can be independently verified. And to eliminate any doubt of identity theft and be assured of the message's origin, this data was signed using the SAS module. Factom provide a blockchain explorer where we can view the chain and entries we have just submitted. I hope this video has given you a sense of how easy Harmony Connect is to use and the importance of protecting against identity theft. Encryption on its own is not enough to dispel any doubts. For real-time data streaming, you would most likely not send every message to Harmony. In our next video, we will be using Signed at Source with Streamer, which is a decentralized publish and subscribe data network.